This video presentation is brought to you by the Pro Mathematics Academy. Welcome back to another video presentation brought to you by the Pro Mathematics Academy. In this video, we'll be looking at miscellaneous calculus questions, right? Just for practice. Okay, so here we start with question number 15, which reads, the function f is such that the following limit exists. The limit as h approaches 0, right, of f of a plus h minus f of a minus h, all divided by h. Okay, what is its value? So to compute this limit, right, the first thing we want to do is we want to take our expression and we want to add and subtract from it f of a. Okay, so here I add f of a and I minus f of a, which keeps my expression true and being the same as before, all divided by h, right? And now what this allows me to do is I can now take the limit as h approaches 0 of f of a plus h minus f of a divided by h, right, plus f of a minus f of a minus h, all divided by h. And by my limit law, I can distribute this limit over these two expressions. So here I now have the limit as h approaches 0 of f of a plus h minus f of a divided by h, plus the limit as h approaches 0 of f of a minus f of a minus h, all divided by h, right? Which means if I evaluate this first limit, I think everyone is able to recognize that this is the derivative evaluated at a, right? But only by observing closely can we recognize that the second expression is also the derivative of f evaluated at x equals a. So therefore our answer becomes 2 times the derivative at x equals a. Therefore our answer is E. All right, moving right along, right, we now look at question number 14, right, which gives us f of x equals x squared times the tan of x. What is the derivative of f of x evaluated at the point where x is equal to pi over 4? All right, so here I'll take my f of x equals x squared times tan of x, right? And I'll try to find the derivative, which here we must recognize that we have to use the product rule of differentiation, which says here I take the first function and multiply by the derivative of the second function plus the second function times the derivative of the first function. So evaluating this gives me x squared times the secant squared of x, right, plus tan of x times 2x. All right, so now we take our x squared. Let's just copy this down. Right, we take our x squared times secant squared of x plus tan of x times 2x evaluated at x equals pi over 4. This then means we have pi over 4 squared times the secant squared function of x plus, well, here x is equal to pi over 4. So that's pi over 4 plus tan of pi over 4 times 2 times pi over 4, right? I can rewrite this as pi over 4 times the secant of pi over 4 all squared plus 1, because tan of pi over 4 is 1, times pi over 2. So now we need to figure out what is the secant at x equals pi over 4. Now recall that the secant function of x is equal to 1 over the cosine of x. So here, the secant evaluated at pi over 4 is actually 1 over cosine of pi over 4. And if we recall from our basic rules of trigonometry, we should remember that the cosine of pi over 4 is equal to the square root of 2 divided by 2, right? So here this is 1 over the square root of 2 divided by 2, which is equal to 2 divided by the square root of 2. Okay? So here we can go back and we can insert this result in our formula. So this means that we now have pi over 4 times 2 divided by the square root of 2 all squared, right? Plus pi over 2. We still have to simplify some more. So this becomes pi over 2 times the square root of 2, because here we cancel this 2 into this 4 2 times, right? And we still have everything being raised to the second power plus pi over 2. So here this becomes pi squared over 2 squared times the square root of 2 squared plus pi over 2, which is equal to pi squared over 8 plus pi over 2. Now we can factor out pi over 2, which then gives us pi over 4 plus 1. Okay? So now we look to see which of these answers is the number we're looking for, or letter, sorry. So here we end up with answer choice B. Moving right along, we now take on question number 13, right? And it's important to recognize that here we're going to perform implicit differentiation, right? So here I'm going to give you method 1, right? So for method 1, we say that we take our equation y times tan of x minus y squared plus 5x equals 0, right? And we differentiate each term in the expression, right? So here we're performing term-wise differentiation, okay? And recall that when we're doing implicit differentiation, we want to always multiply by dy dx whenever we differentiate a function of y, okay? So here, when we differentiate y times tan of x, we're going to end up with dy dx, right, times the tan of x plus y times secant squared of x, right, for our first term, minus 2y times dy dx plus 5 equals 0. And now we try to transpose for our dy dx. So here I'll group up the dy dx's, right? So here I have tan of x minus 2y equals negative 5 minus y times secant squared of x. So this means that our derivative dy dx is equal to negative 5 minus y secant squared of x divided by tan of x minus 2y. And one thing to note here is that if I decide to change around my function, right, I can actually factor out a negative from both the numerator and the denominator. And so I can end up with 5 plus y times secant squared of x divided by 2y minus tan of x. All right. So when we look at our answer choices, we realize that none of these answer choices reflect our answer. Okay, so let's perform one more test, which is method 2, to see if we made an error or we are correct. So for f of xy equals 0, right, the derivative dy dx is actually equal to the negative of the partial derivative with respect to x of f of xy over the partial derivative with respect to y of f of xy. Okay, so we're going to use this rule and we're going to see if we get a different answer or we get the same answer. Okay, so here our f of xy is equal to our equation that we previously had. Okay, well, it's equal to this side. Okay, so now let's go. So the derivative, well, the partial derivative with respect to x of f of xy here is equal to y times secant squared of x, right, minus, well, actually, we're going to have a plus here, 5. So here we have our partial derivative with respect to x. Now we need our partial derivative with respect to y of f of xy, which is equal to, here we're going to treat all the terms in x as a constant. Okay, so that means we end up with tan of x, right, minus 2y. Okay, so now that we have these two terms, we can go ahead and write down our answer. So therefore, dy by dx is equal to the negative of y times secant squared x plus 5 divided by tan of x minus 2y, which is the same as y times secant squared of x plus 5 divided by 2y minus tan of x. So what we're realizing now is that we have confirmed, right, the solution that we previously got in method number 1, which we thought was incorrect, right? But now we see that by using our method 2, right? Method 2, which is not a traditional method, okay? But if we do our research, we can find that method somewhere in the calculus scrolls. All right, so looking back at the solutions, right, moving right along. We're now looking at question number 12. Here we have h of x equals the square root of x raised to the x power, right? And we're asked to find h prime of x. All right, so what we're going to do here, we're going to take the log of h of x, right, which is equal to the log of the square root of x raised to the x power. So this is the same as saying ln y is equal to the log of the square root of x raised to the x, and because of the powers of logarithm, or rules rather, we now have ln y is equal to x times ln of x raised to the half power, which is the same as ln y is equal to half x times ln x. So now we can perform implicit differentiation again on this function, right? So if we differentiate both sides with respect to x, of course, right? So here I'm differentiating my ln y, and I'm also differentiating my half x times ln x, okay? Which means we have 1 over y times dy dx, okay? Here we're performing implicit differentiation, equals half x times 1 over x plus ln x times a half. So now, what do we end up with? We end up with dy dx equals y times half plus half ln x. Okay, but what is y? Y is equal to the square root of x raised to the x power. So therefore, resubstituting in the square root of x raised to the x power, we now end up with something closer to the answer choices that are actually there. So looking at the answer choices, we realize that answer choice E is the correct answer. Okay, and that's simply because here we have the square root of x raised to the x, right? Let's erase that. Raised to the x power times half plus ln of x raised to the half power. So here I can reverse this procedure, right? If I'm multiplying by a constant, I can raise that to the power of x. So I can raise x to that power, okay, in the log. So therefore, we still end up with square root of x raised to the x times half plus ln of the square root of x. All right. Now that solution could have been produced using other methods, but here we just went with what was straightforward. Nice. For question number 11, we now see that we have a function f of x equals sine of the log of 1 plus x squared, right? And we want to find f prime of x. So here, what we're going to be doing is the chain rule, okay? And we perform the chain rule whenever we have a composite function, okay, guys? So here we have a function inside of a function, which is inside of another function that's inside of a function. All right, of course, that sounds like a mouthful. So here, we're going to be taking the derivative of our sine function, right, evaluated at the same thing, right? So here I'm going to keep the log of 1 plus x squared, right, times the derivative now of the inner function. So the inner function was the log of 1 plus x squared. All right, so, which is now equal to, we're still going to have the same cosine of the log of 1 plus x squared times, now we want 1 over the log of 1 plus x squared, right, which is our inner function here, okay, times the derivative with respect to x of the log of 1 plus x squared, which is equal to, because I can't bother to rewrite over all of this, we take it and copy, right? So now we want the derivative of the log of that function, which is 1 over 1 plus x squared times the derivative with respect to x of 1 plus x squared, right? So here we should be able to recognize that the final answer comes down to, from here we should be able to choose from the multiple choices, but just to complete the question, we see that the answer choice becomes D. Okay, moving right along to question number 10. Here we have a simple one. Okay, here we're given the function which maps elements from real except 0 onto real is such that f of x equals x squared sine of 1 over x. All right, and it now asks us to investigate the function at 0. So which of the following is true? A, f has a limit but is not continuous, right? So right off the top, we want to go with A, right? Because that sounds true. Part B says f is continuous there, but the limit does not exist. Obviously, the limit exists, all right? And the function is not continuous there. Part C, f has no limit and is not continuous there. So, it's not continuous there, which is true, but the limit exists, okay? Part D says f is continuous there, which is wrong, and the limit exists. So the limit exists, but it's not continuous there, okay? 0 is not in the domain of the function, and so the question makes no sense at all. Now the question makes sense right? Because in order for the limit to exist, the function does not need to be continuous at that point, right? Or that value does not even need to be in the domain of the function, okay? So that's something that we really need to note here. So that answer choice E is actually something that's there to throw you off. All right, so let's see how we can find the limit, right, as x approaches 0 of x squared times the sine of 1 upon x, right? So let's make a note here. To find this, we need the squeeze theorem. Okay? We need the squeeze theorem. So I'm not going to quote the squeeze theorem here, right? I'm just going to say that since -1 is less than or equal to sine of 1 upon x, which is less than or equal to 1, this implies that negative x squared is less than or equal to x squared times the sine of 1 upon x, which is less than or equal to x squared. Now, we take the limit throughout. Okay? And taking the limit throughout gives us the limit as x approaches 0 of negative x squared is less than the limit as x approaches 0 of x squared sine of 1 over x. Okay? So that's also less than the limit as x approaches 0 of x squared. So this means we have 0 is less than or equal to the limit as x approaches 0 of sine of 1 over x times x squared, which is less than 0. So here, I can now copy this into this section, right, to complete this proof, which means that the limit as x approaches 0 of x squared sine 1 upon x is equal to 0. So therefore, the limit exists. Okay? And the limit is 0. So here, whenever we get these types of questions, right, this is the important takeaway. X times sine of 1 over x, or x squared times sine of 1 over x, or x cubed times the sine of 1 over x. Whenever we get those types of questions, we need to remember the squeeze theorem. Okay? Moving right along to question number 9. So for question number 9, we see that the function f of x is differentiable at x equals a. What do we know? Okay, so once a function is differentiable at a point, what is it that we should recognize? We should recognize that the function is continuous, because once a function is differentiable, it is also continuous. Okay, but continuous doesn't mean it is differentiable, right? Differentiable means it is continuous. Okay, so therefore it's a one-way implication. All right. F of x has a limit at x equals a, of course, because if the function is differentiable, right, then it must be continuous, which means if it is continuous, the limit must exist. So continuity implies that the limit exists. Okay? So here, 1 and 2 seems to be true, and part 3, on the graph, a unique tangent line exists. This is the same as part 1. Okay? So here I'll just say it is the same as differentiability. It is the same as saying that the function is differentiable. So therefore, we end up with E as our answer choice. Moving right along to question number 8. Question number 8 gives us this piecewise function, right? And with this piecewise function, what can we do? We want the function to be continuous, right? So if the function is continuous, then we must have the limit existing at that point, and the limit must be equal to the function. Okay, so here let's try and find the limit. So the limit from the left, right, of 1 of f of x is equal to the limit as x approaches 1 of log x. Okay, well, that is actually incorrect, because log x is the function from the right. So here this is a minus x, which means that if I evaluate this function, right, then it should be equal to a minus 1. Now the limit as x approaches 1 from the right of f of x is equal to the limit as x approaches 1 of the log of x, which is equal to ln, well, here, log of 1, which is equal to 0, okay? Log of 1 is equal to 0. You can try to plug that in on your calculator to validate what I'm saying. So here, if the limit exists, then both of these limits have to be equal, okay? So if both limits are equal, then a minus 1 is equal to 0, which implies that a is equal to 1. So therefore, the answer for this question must be C. Okay? And let's take our last question here, question number 7, right? Which asks us to say what can ensure that the function is continuous at some point x equal a. So here we're interested in having the function be continuous. Okay? Now part A says the limit from the left must be equal to the limit from the right. Okay? Now if the limit exists, this doesn't ensure that the function is continuous. So therefore, this is not the answer. Okay? Next, we say that the limit of the function as x approaches a is equal to L, where L is a real number, right? Now, this is just saying that the limit exists, but we do not know what the value of the function is, okay? We do not know what the value of the function is, so we cannot choose part B, okay? Continuing, it says that the limit exists for f of x, right? So if we know that the limit exists, it doesn't mean that the function is continuous, because the function could be undefined at that point. All right, so that's not the answer. F of x equals f of a. F of x equals f of a. So the function is defined, right? But it doesn't mean that the limit is, it doesn't mean that the function is continuous, even though the function is defined at a point x equal a, okay? So that's still incorrect. Now this right here is the answer. Why? Because this function is telling us that the function is differentiable. Okay, this is telling us that the function is differentiable. So once the function is differentiable, the function must be continuous. Okay, so that's it, guys. That is it for this video. Please remember to hit the notification bell, like, share, and subscribe for future post notification.